All right. So last class, like we discussed about the Newton-Raphson method, useful in optimization. Yes. So we have seen Newton-Raphson method to find the roots, isn't it? In your previous semester, you have seen Newton-Raphson method to compute the roots of a nonlinear equation. And previous class, what we have seen is to use Newton-Raphson method to solve optimization problem. Okay. So before that, since I heard that you were not aware of fractals in your previous semester, so I thought of introducing you to this whole different world known as fractals. Okay, so this is a different world by itself. Why I'm saying this, you will know, you'll get to know soon. Okay, so suppose you have this equation z cube minus 1 equals to 0. All right, so as you know in your R class yesterday, so professor was asking you what is root over minus 1. Yes, so here we will not go to that much history. We will say root over minus 1 is I. Okay, so you know z cube minus 1, z is a complex number, and we want to see what are its roots. All right, so z to the power 3 minus 1 equal to 0. So it will have 3 roots. It's well known. Okay, and these are popularly known as cube roots of unity because they lie on a unit circle. Okay. So 2 of them will be complex, like they will be complex conjugate, and 1 of them will be real, like 1 omega omega square. Okay, so those are the cube roots of unity. I hope you already know about this cube roots of unity in your complex analysis in your class 12 syllabus. Okay. Next, this suppose you take z to the power 4 minus 1 equals to 0. Okay, so like here also you will have 4 different roots, right? 4 different roots. So now, as you already know in Newton-Raphson method, right, in your previous semester, that you already know that this method is sensitive to initial condition. That means if there are more than one root, all right, in your nonlinear equation, if you start nearby root 1, the method will converge to that root 1. Okay, if you start nearby root 2, the initial condition you give somewhere nearby root 2, then your Newton-Raphson method will converge towards the root 2. Okay, but if you start somewhere in between root 1 and root 2, where it will go? Do you know? That we don't know. Is it? It might go to root 1 or root 2. That choice we know. But where exactly it will go, that we don't know. Okay, so this brings us to a topic like nonlinear dynamics. Okay, so as you can see, these equations are nonlinear. Z cube minus 1 equals to 0, z to the power 4 minus 1 equals to 0. These are nonlinear equations. Okay, so therefore, you know, you can expect that there is some complexity involved in this. You can't predict where the root will go, which initial condition you apply to Newton-Raphson method will lead to which root. Okay, so if the equation was linear, it could have been straightforward. Z minus 1 equal to 0. It's a linear root, it's a linear equation, and you know already that z equal to 1 is the only solution, and the whole domain, any initial condition you take, it will always converge to 1. Add the nonlinearity into the equation, like z square minus 1 equal to 0, things get complicated. Okay, so therefore I asked you, z cube minus 1 equals to 0, the solution to the above equation represents the cube root of unity. Yes, fine. Consider this equation, z to the power 4 minus 1 equals to 0. Now we ask, which initial condition will lead to, like, will converge to the 4 roots? Which of the 4 roots? Okay, we don't know. So this is where the role of computation comes into picture. This is a very simple equation, but the moment I reframe the problem, things get interesting, because you can only use computation to find it. Can you do it by hand? Which root goes to where? If I give you a grid and I ask you which root goes to where, can you do it by hand? No, because if you want a fine grid, you will take 1000 cross 1000 grid, right? So how many points you have? 1000 cross 1000. So 10 to the power 6 points. Okay. So even if you take 1 minute for one computation, so it will be 10 to the power 6 minutes. I welcome you to find 10 to the power 6 minutes is how much hours. Okay. So, but there is computation, and computation comes here where it can do within seconds. Okay, and we will see exactly that. Okay, so okay, so as you can see here, like I have written a program to find which initial condition goes to which of the four roots. If it goes to root 1, I will mark it with one color. If it goes to root 2, I will mark it with the second color. Root 3, third color. So I will define four colors here. So as you can see, I have defined the colors here. List of colors: blue, red, green, yellow. Okay. So here I have set the tolerance to be 10 to the power of -8. So how I will know that the root has converged, my initial condition has converged to that root? If the distance between the root and my iterates is less than, absolute value is less than 10 to the power of -8, I feel or I believe that my initial condition is converged to that specific root. Okay. So here is the function I have defined, like as you can see, Newton, it takes the initial condition, that is Z0. F is our function we have defined, that will be Z to the power 4 minus 1. F prime is the derivative. You already know Newton-Raphson method depends on the derivative. Yes, the function should be differentiable in order for the numerical method to work. Yes, so we need F prime detail and we are iterating for 1000 times. Yes, okay, so here it is written. I will share the code with you. So yeah, Z equals to Z0, fine. Here I am computing the, so what is the Newton-Raphson method? Zn plus 1 equals to Zn minus f of Zn divided by f prime of Zn. Yes, so that part I am doing. Zn plus 1 equal to Zn minus whatever part is there, that I am showing at dz. Okay, dz is f of z divided by the derivative of z. Yes. Now I am checking if the root is slowly approaching, if the initial iterates are slowly approaching to your root, then the dz will be small. Understand, Zn plus 1 equals to Zn plus something or minus something. So difference between Zn plus 1 minus Zn should be less than a tolerance. Okay, so that is what I am checking very cleverly here. Okay, I'm not checking the iterates, but I'm checking the dz. Okay. So if the dz is less than the tolerance, then we have converged to the root. So just return the root, return z. Okay, so here is the fractal I am showing in. So I have shown my grid from -1 to 1, x-axis, -1 to 1 on y-axis. Okay, right. So I'm defining like a matrix over here, M, fine. Okay, so there are a lot of some big things going on here, but you can always look into it very close. Try to find what is the use of this where is close all these comments. This is your chance to understand why these comments are useful. I think you are seeing this for the first time. Nothing, like I'm appending the roots, that's it. So every time I find a root, I'm appending those roots. I don't want to you to get involved in all of this jargon, but main thing, just the idea I will communicate to you. So here I am defining like from -1 to 1, x min is -1, x max is -1, y min is -1, y max is 1. So in between that, we're using two for loops. I am dividing the grid, okay, for n times, that is 200 cross 200 grid. I could have done 1000 cross 1000 grid, but it will take a bit of time, 4 minutes at least. So Z0 is defined. This is the initial condition I am taking. So you can understand that what I am doing right now is this. So you have -1, 1, -1, 1. Okay, this is your x0, this is your y0. And each point you take, this is x0 plus I y0. Okay. Yes. So using these two for loops, using the two for loops, I am creating all these different initial conditions. Is it? And I am checking where each of these initial condition converts. R1, R2, R3, R4. Like, and then I will assign the colors to it. Okay. Then we will see, then we will mark each of this initial condition with the color. Okay. Then we will see what entire colorful picture looks like. How many of you think that it will be just like normal picture, like with a combination of just 4 colors? It will be obviously a combination of 4 colors, right? Because anywhere your root will be converging to the 4 roots. So I am asking you to guess how so now you know that the picture will be colorful, comprising of 4 colors. I am asking you how this picture might look like. If I tell you that somewhere here there is one root, somewhere here there is another, somewhere here there is the third, there is the fourth. So you already know that nearby this, it will be, suppose I assign green, red, yellow, then other was which color? Blue. So nearby these, it will be these colors. So what about these things here? Can you imagine how it looks? So that is our motivation, like how the picture looks. So this is what we are doing here. Z0 you have defined x plus yij here. Okay. Then you are pushing that initial condition into the function Newton. Okay. So what you will get from here is R. What is the R? So what does Newton do? Let's see. Yes. So it will return Z, the root. As you can see, the function define Newton, it returns Z, right? So it returns one of the root to where it converges. So the moment you pass this initial condition here, Z0, it will give you R to the root which it has converged to. Okay. Now, if R is not false, fine. Get the index, like to which color should I assign it? Okay. You have seen if it is like I have defined a list of colors. 4 colors I have defined. So if it is root 1, it will go to the list 1 color. Okay. Root 4 means 4th color. Okay. Fine. So yes. So yeah, that's good. Yes. So anyway, so this is the basic idea. Others are just beautification and all those things. Okay. Here I have already sent because I did not give the liberty to the derivative for me. I have to explicitly say what is the derivative. So you can see below that I have shown f equal to lambda z, function z to the power 4 minus 1. F prime is 4z cubed. That's it. You can guess. So this is how it looks. Okay. And it is a fractal. So why I am saying that it is a fractal? As you can see intuitively, we already know that these 4 roots will have a single color associated to them. Therefore, you can see here, this left side here over here, yellow color, there is one root. So you can expect the nearby points to converge to that root, and hence it will be colored yellow. Okay. Similarly for the blue. All right. Those points which converge to that point will be marked blue. Okay. So these all points are very easy to understand. But things get interesting nearby these points. If you just zoom in here, if you take some point here, somewhere here, can you predict which color it is? Here, somewhere here. Can't predict. Okay. So that's how it is unpredictable. Okay. Such a simple equation, but it is highly unpredictable to find which root it will converge to. So the moment you say, I know everything about this root, think about it. I just wanted to show this, how this simple equation can give you such a beautiful image. So some of you might be wondering, what if I can zoom in? The logic is I encourage you to zoom in. Don't take -1 to 1. Take somewhere the grid where you want to zoom in. Suppose you want to zoom into this section. So take like 0.0 to 0.5, 0 to 0.5. Then it will give you the zoomed version of this part. Okay. So this is a fractal. What is a fractal finally? What is a fractal? Fractal means, as you can see, frac word is used. It's a fractional dimension. Okay. It's a fractal means coming from fractional dimension. You already know what is 0 dimension, what is 1 dimension, what is 2 dimension, what is 3 dimension. Even you know now what is 4th dimension. But do you know what is 2.5 dimensions? Okay. So therefore, like you can think of this fractals as like roughness. Okay. You can feel your what you call the desk. It is quite smooth, but still it has a roughness. Okay. Like I can say to you, like mountains and all, they have a roughness. So therefore, never anyone who draws mountain like this, not a good drawer. Okay. Mountain is never like this. If you draw mountain like this, you are saying that mountain is smooth. But in real world, do you see mountain is smooth? No. It always has this trees, it always makes it non-smooth. Okay. So therefore, fractals like is not only a mathematical concept, rather than you can see it like in real world also. So fractal was one of the videos which I saw during my bachelor's degree after my class, after my data structures class. Okay, I was in my hostel room and I was watching like some videos, like YouTube videos and all. Then I came across these fractals. And fortunately, I was fortunate that I saw a video by Mandelbrot who discovered this fractal geometry. And after that, I was completely submerged into it. So I was so much submerged that I don't want to even study my degree courses. Okay. But then I realized, no, I have to pass. So I studied those courses also. But there, my journey began for nonlinear dynamics and fractals. So which is going till now. Okay. So it has been like 10, 12 years now. So it has been going till now. So therefore, small things can excite you. Small things can ignite a spark in you, which can totally change your interest. So therefore, believe in that and don't skip what you're interested in. So this is one of the fractal. It is known as a Newton fractal because it has been derived from the Newton equation Z4 minus 1 equals to 0. Okay. Now I will show you some mind-boggling fractals. Okay. So one of them will be the Mandelbrot set. Let me. So this is a website where you can find this fractals useful JS. There are a lot of different websites. You can always play with these fractals. In Western countries, they usually put fractals in their dresses. Like, it creates a beautiful dress and they wear it. Okay, I really want that to come to India. So, yeah, I just want to show you the zoomed out image of this. What is a Newton fractal actually? But it's, yeah. So this is a Newton fractal, okay? And it only comes from a very simple equation. Yes. I encourage you to search on Wikipedia, like Newton fractal, okay? Also like Mandelbrot fractal. Also maybe Julia set. So these are like highly remarkable mathematical images. So how you think that in video games which you are playing, they generate such a nice graphics that you really believe that it's an aeroplane or it is a tree, which you know. Okay, it's a tree that just like a tree like we see real life. So they use fractals to create it. Okay, I'll say more about it. But as you can see, this is a fractal image. Okay, so I want to zoom over here somewhere. Okay, let's zoom in here. So every time it will do a computation. So therefore you can see this bar going in. So as you can see, these are self-similar structures, okay? Self-similar. The moment I zoom in, self, again and again, those structures will prevail. So fractals means self-similar. And the moment I zoom in the white one, it will be that Newton fractal, okay? So let us zoom in somewhere here. Can I do that? Yeah. So as you can see, this looks lot of like an Amazon forest or something like that. Okay. So yes, so let us zoom in one more. So this requires a lot of heavy computational skills to generate all these images. Some things like Magma, all these, there are different softwares. Okay. You have to use these things. But it's pretty interesting, which I think like one should cover if they're telling about root finding methods. I am not able to see. Okay, so it's not the only fractal. Yes, so the moment you zoom in, zoom in, zoom in, you will see all these images. Okay. The beautiful fact about this is, can you imagine where these kind of things actually comes into place? You don't have to be in Earth, on Earth. You have to go above Earth. Like just travel, feel like, think that you are traveling in a rocket and you're seeing Earth from below. Do you imagine some things like this? Hmm? Yeah, something like that. Yes, galaxies you can say, but I'm saying it's on the Earth only. So, yes. So how do you think they measure the coastline length of coastlines? So using fractal geometry. So fractal is a whole different geometry. Okay, it's a whole new geometry. Okay, and it comes as a byproduct of chaotic dynamics. Okay, like chaotic dynamics, you can't predict the dynamics of any event. Okay. Before that, like yes. So does that represent something like this? Yes. So you can see how self-similar it is at different scales. Okay, but how you can actually find the length? They can only use it via fractal geometry. Okay, they can collect the data, scale it down. Obviously they will collect the satellite images, they can find the boundary through data points, and then they will have the data points, they can put into fractal geometry concepts and find the length and then scale it accordingly. Okay, so this is one. So this is how like these are known as a fractal coast. I think at some point of time it might have caught you in brain why they actually look like this, why this coastline actually look like this and not look like something like simple, just like this, right? Yeah. So that's what real world geometry is. Real world geometry is not rectangles and all these things. It is fractal like. Okay. Some more examples I want to show, like how many of you have eaten broccoli? Broccoli or cauliflower? Broccoli. Okay. So do you think broccoli is also like a fractal? Yes. So you can see, like, even if you take a small part of it, it will, if you zoom in, it will look like a bigger part. Okay. And if I tell what is the fractal dimension of broccoli, okay. So there is a fractal dimension to broccoli, like every fractal has a dimension to it. So as you can see, so researchers have already found out the, fractal dimensions of a green broccoli and a white cauliflower. Okay. So if it is a fractal, then what is the fractal dimension? Okay. So they have actually shown that it is a fractal. The food you are eating is actually a fractal. Okay. And it has a fractal dimension of 1.78. It's not one dimensional, it's not two dimensional. It's somewhere between that, 1.78. Okay. There is a way, and there is an error also, 0.02 plus minus. So this is what. Okay. And yeah, there are many things. I will share the link to you. Not a good audio. Okay, you can explore this. I will share the link to you. Okay. So yes. So this is another fractal discovered by Julia. This was discovered by Newton. Sorry, Mandelbrot, known as Mandelbrot fractal. And this is by Julia. Okay, Julia set. If you open it on Wikipedia, you can see. Yes. So Julia set. Yes, you can see this video over here. So the more you zoom in the self-similar structures you see. So you can feel like how much computation time it would have taken to generate this video. Okay. So yeah, you can find all these things here. Like you can see how math and computations are going hand in hand to generate these beautiful images. Okay, I leave it to you to find. And yes, what I wanted to cover. Yes, there is a good book also, like so there is a nice book. If you want, I can share a PDF. Just ask me, like, if you need. So this is a very beautiful book, like which covers a lot on fractals. So this is a heavy oily printed book, and I have a PDF of it. So yes, you can buy it also. So I encourage you, if you're interested, just go to it and search. So yeah, it's a very nice book. Like you can appreciate the fractals better. As you can see, it's Indra's Pearls, the vision of Felix Klein, like who has written it. So yeah, it has all these pictures kind of, and yeah, how you will generate fractals using coding and different things. Okay, so with that, I think the fractal journey has come to an end. Okay, so this is out of a topic in the course, but I thought of saying it. Okay, so should we return to our course? Okay, so last class we have discussed about Newton-Raphson method, right? I was thinking that we can solve some problems before we go to another method. Okay, so this is a bit of like a practical problem. Okay, let us start with a basic problem, then we'll go to that. So suppose you have a root, like this is a question we'll start with. So Newton method of optimization. Function. Okay, suppose we have a function fx. It's just a one-dimensional like function depending only on x. Later on, we will see a function of two variables, which is a function of like x and y. Okay, so fx equals to 3x cubed, suppose minus 10x square, 56x plus 5. So can you tell me like can you find the minimum and maximum of this function using Newton-Raphson method of optimization? So find the min and max of this function. I'll give you the range, okay, to this. Maybe you can take minus 4 to 6. X belongs to say minus 4 to 6. can do this problem and then to observe that when you do this iteration, okay, you have the record of the iterates xn and also f, the function evaluated at those iterates, f of xn. Moreover, you have f prime and f double prime. Now, can you say by looking at the sign of f prime and f double prime that it is a maximum or a minimum? F prime is positive or close to 0, that's fine, 0.00. But f double prime is negative. F double prime has been negative so long. So you can say that at this point you have a maximum. Yes, because f double prime is less than 0. You already know the theory that if f prime is 0, if you set it to 0, you will have two roots like minimum or maximum or extremum. For it to be a minimum, the second derivative should be greater than 0. For the extremum to be maximum, f double prime should be less than 0. Yes. So you are getting f double prime to be less than 0. Hence, this is that extremum point, but the value at that point is the actual function value. So what is the minimum value of the function? What is the minimum value of the function? Is this? This is the minimum value of the function, right? Sorry. Yes, yes. Okay. Yeah, so this is the maximum value of the function, is it? So now you see how you can actually find this maximum value by using Newton-Raphson. But that's not the end of the story yet. This function also has a minimum. Okay. So if you start with x naught equals to 2, which you will do it now. Okay. After that, Rick. So this is just do it with x naught equals to 2 and finish it off and see that it actually converges to something different. Okay. Then we'll have another observation. Okay. Observations. So as you can see, f double prime here is positive, which was negative before. Yes, this was negative before, but now it is positive. Okay, f double prime is positive, but and also at a different value. Also at a different value as compared to this. So what does it suggest? F double prime is positive at this value at x equals to 3.8419. So it says that this is minimum. Yes. So this is the minimum point, minimum x point, and this is your minimum value. Now, can I ask you to maybe plot this function? So if you plot this function, okay, then only you can actually see that there are minimum and maximum, right? So check if you draw it in like maybe Desmos or Python, just a one stroke you have to need like f of x and this is x. Yeah, you will get something like this, some function like this, okay? All right. So obviously this is not 0. This is not 0. This is minus 200. Okay. This point is minus 200. And you have to pick your axis like from minus 200 to 100. Don't take it from 0 to 100. Minus 200 to 100. Then you can appreciate. So what we did. So some 0 is somewhere here. 0 is somewhere here. Okay. You can check. Then we took minus 2. 0 as the initial guess. Okay. And then we got maximum at this point. So you can see that we maximum here somewhere. Okay, suppose this is minus 2.8. So you can see this is a proper initial guess which was near to minus 2.8 and hence it got converged to this. Okay, next initial guess what we took 2. So 2 is somewhere here. Okay, and your minimum value is 3.84, which is somewhere here. You can see how these picking these two different initial guesses converge to these two different minimum and maximum of the function. Okay, so you can appreciate better that Newton-Raphson method here also in optimization is strongly dependent on the initial guess. That's one of the demerit of the Newton-Raphson method. It depends on the initial guess, and you don't know how the function looks or how your data looks. Okay, So that's one of the demerit. And second demerit of this is you have to find double derivative of the function. Without double derivative, this method can't work. And computing double derivative is expensive. Computation is expensive also. This is simple function, but if you have a more complicated transcendental function, then it is more complicated and difficult. So these are the two difficulties. If we ask what are the demerits or difficulties in Newton-Raphson method in optimization, what you will write? Two methods, 2 points. One is it is strongly dependent on the initial guess. Second, you have to compute the double derivative, not only the single. The function has to be double differentiable. Okay. So these are the demerits and merits of Newton-Raphson method for optimization. Okay. Cool. So you can take a break. So last two classes we talked about one-dimensional unconstrained optimization problems. Okay, so obviously we studied one-dimensional optimization problems like a function depending on one variable. Yes, and we saw how to optimize it, how to find minimum, how to find maximum of that function. Yes, so we used like till now the Newton-Raphson method to solve for the optimization problem. The main problem we faced is in this method, we have to find the single derivative and double derivative. Okay. And then we derived the Newton-Raphson formula. But before that, I showed you that there are few kinds of methods like optimization method. Some involves derivatives, some doesn't involve derivatives. Okay. That is like random search. Something like random search I did not cover because randomly you just take an initial guess and take random points without any logic. Okay, just take random points and find the value of the function, compare it with the previous value of the function. If it is minimum, yes, else, yeah, keep on searching. Okay, so that's random search, like a brute force method, not that effective. Then we have a golden section method, which I'm saving it for some time. And some involve derivative like Newton-Raphson gradient descent method. Okay, gradient descent method will be the final method of this chapter. So we will cover the multi-dimensional unconstrained optimization problem now, which will involve gradient. All right, and second derivative like Hessian. So you can do d2x, d2y by dx2. Okay, if y is a function of x. But how you will do it if your y is a function of more than one variable? There you have to go for gradient. Okay, Hessian, if it is a double derivative. Okay, gradient, you know, grad f, del 2f, it's like Hessian. Okay, so we'll deal with those kind of things in this lecture. If time permits, we'll go to golden section, or maybe we'll cover golden section in the next class. Okay. So golden section method is the next method for us after this, and gradient descent. So these are the two remaining methods for the optimization module, which we are discussing. Okay. After that, we will begin with artificial neural network. Okay. So, yeah. As we have discussed previously, like Newton-Raphson method is a gradient-based method, of course, because there is some derivative involved. And what we discussed is Newton-Raphson method for one dimension. Why is just a function of one dimension. A previous just example, we considered f is a function of x only. We never considered f is a function of x and y, but now we will consider it. Okay, Newton-Raphson method requires a function to be twice differentiable. That's one of the demerit. Okay, the more function. So this is what we are heading towards golden section. Golden section is not that an efficient method, but why we are learning it is it uses golden ratio. Okay, it uses golden ratio. So I encourage you all to study a bit about what is golden ratio. You can see in sunflower, like the patterns in a sunflower, okay, how they are distributed is actually like Fibonacci sequence. And if you take the ratio also, the golden ratio comes into picture. Okay, so some good architectures and all, they have this golden ratio in mind. So I want you to actually search what is the golden ratio and know how they derive that golden ratio. Okay. section method. While beginning the golden section method, I will directly say that we will take the ratio to be golden ratio and this is. So, but before that, you have to know what is a golden ratio. So I encourage you all to, so it's the most irrational number. The most irrational number is the golden ratio. You can see how irrational numbers can help us in designing a lot of, like, we don't know, like in nature also, till now it is not known why in nature, why in sunflower, like it's a beautiful flower. Why in such a beautiful flower we have this pattern of sunflowers, like the golden ratio comes into existence. Till now, it's hidden. So these are like the hidden geometries of nature, right? It's not yet uncovered. But why it has to be golden ratio? Okay. So therefore, then optimizers like optimization scientists and all, they thought like why we can't use optimize this ratio optimization in our optimization algorithm. And when they used it, they found that the method turned out to be efficient. Okay. So that's what we are doing, right? We take the natural organic products for our health. Yes, so that's the belief. Yeah. So yeah, Newton-Raphson method is fast, accurate, but it requires a good initial guess. This motivates us to learn more about Newton methods. There are a lot of different variant of Newton method which will be said by the project presentations. One is quasi-Newton method, and one is a Brent method. Okay, Brent's method will be covered by one group, and the other group will talk about quasi-Newton method. That is like PBFS method, something. So much about it. So method. These are the methods that avoid the drawbacks of the Newton method, but they behave like Newton method. Okay, they behave like Newton method, hence quasi-Newton method, but they avoid the drawbacks of the Newton method. Okay, so therefore, after learning Newton method, it's a well-known fact that you should study about quasi-Newton method. But I'm giving the opportunity to student. Okay. So before that, we will, so now we will talk about multidimensional. Okay? Multidimensional constraint. I don't have to write unconstrained because that's the only thing we are studying in this module. Multidimensional unconstrained optimization problem. So as usual, we are suppose we are minimizing. We minimize y, which is a function of x. But here rather it is not just a function of x. Rather, x will be a vector. Okay, it will be just not one variable, but more than one variable. And to accompany them together, we make it as a vector. Okay, y is a function of x. Of course, x is a vector that is like, say it has n components in it. Rn, x is a vector in Rn. Okay, what is the function f? So what is the input? Input is obviously Rn, a vector in Rn. And what is the output? It is y. Y is a scalar, so it will just be R. So you can see it takes n-dimensional vector, which is x bar, x vector, and the output is y, which is a real number. Alright, so we can write this x more clearly, like it is just like an array, like you can have x1, x2 till xn, and then we take a transpose maybe. So it will look like a column vector. So this is the magical concepts what programming languages use. MATLAB, which is totally dependent on MATLAB, means anyone knows what is MATLAB? What's the full form of MATLAB? So full form of MATLAB is matrix laboratory. Okay. So MATLAB totally depends on matrices. Everything it does is matrices. Even a number you write, it is a 1x1 matrix. Okay. Any number 3, suppose it's a 1x1 matrix. Okay. So any solving things, whatever you give, is possible due to matrices. Matrices are very powerful things. And that's what is used in Python and any other programming languages take. Big things, big data sets, 1000 data sets, and all will be stored in form of matrices. And then just you have to take the inverse and all. So just before last class, I think we discussed about Penrose generalized inverse. Okay, so that's a very important problem. So please make sure that you do it, not of course by a computer, but make sure you do it via your calculator. You should be knowing how to compute that inverse in calculator. Okay, that's the major step which compute it by hand. Make sure how to compute that inverse in calculator. So go to YouTube, search something like how to compute the inverse of a matrix in calculator, in scientific calculator, in Casio or whatever you have. So it will give you a method and so learn it. Okay, how to do it. So it's a very probable question. So you have this vector, okay, n-dimensional column vector. Now we are minimizing, suppose. We are minimizing. So what is the necessary condition for finding this minimization and a sufficient condition? So what is the necessary condition? So the necessary condition for minima is like, can you guess what it should be? What it should be? See, we were doing derivative of f equals to 0. Okay, derivative of f equal to 0 to find the extremum, right? Now, what is that similar analog here? What is the corresponding analog in a n-dimensional, like multi-dimensional optimization? What is the n-dimensional analog of derivative? We already have seen this. Any guess? The gradient. Okay, the gradient that acts like a derivative in multi-dimensions. Okay, so grad f, you will set grad f to be 0. Okay, is it true? See, grad f derivative used to be a scalar quantity, but grad is a matrix. Gradient is a matrix. Okay, so it's a vector. Okay, so this 0 is not actually 0. It is very tempting to write it as a 0, but actually it's a vector. Okay, these are the small things usually they might not say to you, or you might miss it, but these are very important hidden concepts. Okay, so is the statement still okay? Do you think the statement is correct? Or I have to write something more? So you have to evaluate the gradient at some point. Okay, you have to evaluate the gradient at some point. And what will be that point? That will be the maximum point. So say denote that vector as x star. Okay, that is, how can I write that? You remember that argmin concept we discussed. We never use it in one dimensional, but the moment you are entering into multi-dimensional space, that argmin concept will be used. I think you remember that concept, right? Argmin. Yes, I discussed during the first class, I think. This one. Okay. Argmin. Okay, the same thing you will write here. So x star will be written as argmin of fx. So collect all the x at which fx is minimum. That's the what I mean by argmin. Okay, it will transverse. It will go through all the vector x, and it will compute fx, and it will find where f is minimum. For those value of f, we are gathering the x values. Okay, that's what this simple statement argmin does. Okay, so therefore we have this x star, and we will evaluate the gradient at that x star. Equals to 0. So this is just a necessary condition for the existence of the local minima. What is the sufficient condition for its existence? So there is an extra condition for that. So here we will write about like the necessary and sufficient condition. So this is the necessary and sufficient condition. So there will be one more condition addition to the gradient. Okay. So of course you will evaluate the grad f is equals to x star vector equals to 0. Okay. Further you need one more condition, that is the second gradient, that is del 2f. Okay. Del 2f evaluated of course at the same point x equals to x star. So will this be a matrix, you think? Of course this will be a matrix in multi dimensions. Always think of matrices in multi dimensions. Never think of scalars in multi-dimension, else it will be trouble. So always think about matrices when it is coming to multi-dimensions. So when it is multi-dimension, don't think of 3D space. Think about in terms of matrices. Then many of the things will be easier to visualize and understand. Okay. So this will be a matrix del 2f at x star. Okay. And this matrix should have a special property. Yes, because we are finding the minimum, right? It cannot be any other matrix. Okay. So what it should be? It is not that easy to guess. Okay. So this is basically a theorem or a criterion. Okay. So del 2f evaluated x equals to x star should be positive definite. Okay. How many of you have heard of this positive definite? Positive definite matrix. It's not that easy concept. But is the theorem which helps us to solve many regression problems and all. So of course you can't neglect it. You have to accept that there is something known as positive definite matrix, and you have to learn. So these are very useful matrix. So what is a positive definite matrix? It's a special matrix for which all eigenvalues of that matrix are positive. Simple. Simple. So positive definite sounds like a bigger thing, but the moment you convert it, the concept into eigenvalues, it becomes simple. So what is a positive? Suppose A is a positive definite matrix, then what is its characteristics? Of course, the matrix A will be having its eigenvalues. Okay. And if all the eigenvalues of that matrix is positive, then we say A is a positive definite matrix. Okay. Simple. Yes. So there is a criterion for it. Like if also we'll have all positive eigenvalues. All positive eigenvalues. Okay. Then to write this, so you can take like this is a concept from linear algebra, but I will just write it here. Okay. So if something is positive definite, what we do is we will take any vector like y vector. Okay. Say we take the transpose. Okay. Then we take the matrix which is being said to be positive definite. Okay, what is the positive definite here? Matrix del 2f. Okay, write that here. Okay, then multiply it by y again, the vector. Okay, it should be greater than 0. Not just for any special y vector, but for any y vector. Any y vector you take. Any y vector, up to you. So for any y vector, for any y in your Rn. Okay. Of course, you can't take it 0. If you take y to be 0 vector, everything multiplies to 0 and this is violated. So y vector cannot be 0. Okay. So any issues still so far? So I think this was a bit sudden for you. So I will rewrite it again. A is positive definite. If all the eigenvalues of A are greater than 0, fine. But a more easier test is this. If for any vector, so A is an n cross n matrix, right? N cross n. So any vector, like it should have n components, else it is not able to, you are not able to multiply, right? So n y vector should have n components. Okay. So for any vector y in Rn, have y transpose A y greater than 0. Okay. For any y vector. I am saying greater than 0. That means this must be a scalar, right? This quantity must be a scalar. Of course, you have to do a bit of like check that you will actually get a number here. Okay, that's the idea of multiplying on the right by y, on the left by y transpose. Okay. So it's just like something like yesterday's class in R, like you have a vector here and you have a column vector here. It's like multiplying this. Okay. So that's one of the visualization you can make, that this quantity will actually be a scalar. Okay. So this is the idea I wanted to give it to you. So actually how this gradient and Hessian, this I did not talk about it. So how this gradient will look like? So grad f is known as a gradient. All right. How it looks like. So grad f. So you are differentiating with respect to x1 to xn. Okay. So you will have dou f by dou x1, dou f by dou x2, all with respect to different variables till the last variable dou f by dou xn. And then you take transpose. This is a column vector. Okay. What is, so this is gradient. Now you can do similar to grad to f. This is a special matrix known as Hessian. Okay. I think you must have come across in your predictive analytics class, is it? Hessian? No. No. Hessian. How you learned about gradient descent? You did not learn gradient descent in multi-dimensions. So how gradient descent looks? Sorry, how Hessian looks? How Hessian will look? Any ideas? It's not that trivial, so I'll write it here. Just notice, so whatever I'm writing here will have a pattern to it. So there is nothing more. So everything is by brick we are making the method. So follow it. So just see the pattern here. So here I'm differentiating with respect to x1, okay, 2 times, and the whole diagonal will be like that. So there will be, this is 1 cross 1 position, right? There will be next row, second column, third row, third column. All the diagonals will be of the form I comma I. Yes. So those diagonals will have with respect to all the different variables, x2 square. This is the diagonal I am writing, dou 2f by dou xn. Yes, all the diagonals will be like this. All the diagonals will be the values of your gradient. Is it? So how can we fill the other elements of the matrix? So it will involve the mixed derivatives now. So here we have covered all the second derivative with respect to each of the variables. Now other entries will be just the mixed derivatives. Okay. So like it's like pairs. So you can write dou 2f by dou x1, dou x2. So same thing will go on. See the pattern here. Can you see the pattern here? So on the first row, dou x1 is there. Here in the first row, I took the derivative with respect to x1, then I again took the derivative with respect to x2. Okay, that's fine. That's the 1 cross 1. For the second element, I differentiate with respect to x1, then I differentiate with respect to x2. So x1 is fixed. X1 is fixed. Every time you will see x1, but the next pair will be x2. The next pair will be x3, x4, so on till xn. Yes. So the same thing like you will see. So what can you say what we will get here? So along this column, like it is a bit different. It will be different. 2f by dou x2 dou x1. Okay. So same pattern you can follow. Now the x1 is on the last side. Okay. So same pattern if you follow dou x3 dou x1 so on till dou 2f by dou xn dou x1. Can you see the pattern? Okay. Can you help me with the second row? Can you help me with the second row? What should be the last element here? So it will be dou f, dou 2f by dou x2, dou xn. So you can see another way of visualizing this is, think of these elements. Think of these elements on a dial clock. Think of these elements on a dial clock. Like dial means like this. It's a dial clock. It has a 3D structure. I'm not able to draw it here, but the fact is like these are the elements. These are the elements what yeah. These elements what you see. This element will be this. Okay. The next element will be somewhere here. Okay. And you can arrange all these elements. So you can see that you have this double derivative here. Okay. Once it makes a rotation, the next row, if it comes, it will make a rotation. So this element will shift to the next side, that is here. And since it is a boundary, so the previous element comes back. Okay. So you can think of, so that's the reason why you are having all this quantity on the diagonal. Every time you go to the next row, your dial gets shifted by 1, 1, 1. So if shifted by 1, you are coming here. It's shifted by 2 again, so it's coming here till the last. Okay. What happened to the last element? So it will come to the front. Okay. But the values are different. The notations are different. I'm saying just for you to visualize, like how you can visualize the dial. Okay. That's one of the way to do this Hessian, to understand the Hessian. Okay. So can we say for 2 dimensions? Let's not go to higher dimensions, but at least for n equals to 2. For n equals to 2, that's a 2-dimensional problem. That means your function is dependent on 2 variables, x and y. For n equals to 2, can we reduce all the concepts what we learned here? So you now learned for multi-dimension, n-dimensional. Even if you are given a function in n-dimensional, you now know how to find the minimization condition. What is the minimization condition? Grad f should be equal to 0 and the Hessian should be a positive definite matrix. That's it. Okay. So now you know a theorem for the n-dimensional case. Okay. So yeah. So for n equals to 2, can you bring it down? Can you bring it down for n equals to 2? So for n equals to 2, like yes, for n equals to 2, there is much of a simpler version. Okay, because n equals to 2 much comes in our real world scenarios, like 2 dimension. A function obviously depends on 2 or more variables. So for 2-dimensional, at least you should know this concept. So this is known as Sylvester criterion. Okay. So for n equals to 2, he has formulated a very nice criterion for you. So most of the problems what we will deal with next is depending on this one, this statement. You need to have del 2f to be positive definite, which we already know. Yes. So it gives you like problem at hand. Okay, you have a multi-dimensional problem at hand. That means what? You will have an n cross n matrix. Yes. Usually for that n cross n matrix, it's very difficult to find eigenvalues. Okay, so how you will actually determine that that matrix is positive definite? So it is well known here that your del 2f should be positive definite. But how actually in real life you can, like in computation and all, you can actually find that it is positive definite? Solving the eigenvalue, finding eigenvalue for 2 cross 2 matrix is easier. Okay, but 3 cross 3 matrix, it will be very hard. Forget about n cross 3. So how you will actually check that a matrix is like Hessian is positive definite? That's where this criterion is helpful for 2 dimensions. For higher dimensions, it gets very complicated. Okay, but for 2 dimension, it is worth teaching in class. Okay, so that is like a Sylvester criterion. Okay, So it tells us when grad 2f is a positive definite matrix. So grad 2f is a positive definite matrix if there are two conditions. So one, we need to have like the determinant of that del 2f should be greater than 0. And there is one more condition. There is one more condition. So with respect to the first variable, the second derivative should be greater than 0. Okay. All right. So that's like the first element here. Okay. So I can give you an understanding why this guy can be 0, greater than 0. You know, how many of you know that determinant of a square matrix is product of eigenvalues? You must be knowing it. Trace is the sum of eigenvalues, determinant is product of eigenvalues for a matrix. So if I told you grad 2f Hessian is a positive definite matrix, which means all eigenvalues are greater than 0. If all eigenvalues are greater than 0, what about that product? It's positive. So that's what I meant by writing this. Determinant of grad 2f is greater than 0. So you can just by intuition feel that this pattern is getting satisfied. Okay. So now you know this condition. Now we can solve a problem like an example. So your job is to minimize a function which depends on two variables, f of x comma y, given by this. Okay. So how can you attack this problem? So what grad f looks like here? Grad f will be just dou f by dou x, dou f by dou y transpose. Is it? What is grad 2f? So whatever you have seen in the ND case, can you boil it down to the 2D case and write the form like expression for Hessian? Grad 2f will look like del 2f by del x2, del 2f by del y2. Those are our two double derivatives without any mixed variables. Then we'll have mixed variables, that is dou 2f, dou x, dou y, then y by dou x also. Okay. So can you evaluate these quantities for me? After evaluating this quantity, what you have to do? Of course, you have to set grad f to be 0. After you set grad f to be 0, you will have a simultaneous equation. Of course, the two rows you have set to 0, simultaneous equation. So from that, solving the simultaneous equation, you will get what is x star, y star, which acts as a candidate for the minimization. Yes. But then how you will actually check that it is a minimization, like minimized quantity? For that, you have to check the Hessian also. It should be positive definite. This Hessian should be positive definite. For that, you have to check the Sylvester criteria. Okay. That means after you evaluate this is the first step. After you evaluate this, what you have to do? Compute the determinant of the Hessian, check the sign, first condition. Then the second condition, like dou 2f by the dou x1, which is what is the x1 variable? X first variable. So dou 2f by dou x2 should be greater than 0. Those two conditions are satisfied on. This is necessary. This is sufficient condition. Can you compute this? It will be pretty fast. So what is grad f you got? So grad f is, I'll write it here, 2x minus 2y minus 2, then minus What is Hessian? Hessian is 2. So check like your Hessian is a symmetric matrix. Hessian is symmetric matrix. Okay. And yeah, check if it is the case. I might be wrong. Check if Hessian is always symmetric. And then what you do, you set the grad f to be 0. From there, what you get? You solve it and you get x star equals to 2, y star equals to 1. But that's not end of the concept. That's not end of the concept. What you have to find, you have to check. Step 2 is to check whether the Sylvester criterion is satisfied or not. Check whether the Sylvester criterion is satisfied. Because that's the sufficient condition for the existence of the minimum of a multidimensional function. That is especially two-dimensional function. Okay. So without that, that means there are cases where even if you set grad f to be 0, that's not a minimum. Okay, if Sylvester condition is not satisfied. So what's the derivative we are getting? So you have to compute the derivative of the Hessian. So derivative of the Hessian, that is grad 2f, determinant of the Hessian. So what you get, that comes out to be 12, and that is greater than 0. How you compute the derivative? 2 into 4. Oh, did I do something? So that is like 2 into 4 minus 2 into minus 2. So 8 minus 4. So that is 4. Okay. Is it wrong? 4, is it? So you should correct me whenever I'm doing a mistake. Okay. So it should be 4 greater than 0. And what is dou 2f by dou x2? That is 2. 2. So both are greater than 0. Hence, this is satisfied. So hence, we can say that the minimum point is x star comma y star given by 2 comma 1. Okay. At this point, your function is minimum. What I suggest you to do is plot this function in Python. Okay. Plot this function in Python and visualize actually that it is true. Actually, at x equals to 2 comma 1, you are seeing this. Okay. Okay, so all good so far. Now we will apply this concept to a regression problem. Okay, apply the concept of multidimensional optimization, unconstrained optimization to regression, what we have already studied. So therefore, this you don't really know when any concept you are studying here might be related to some other concept which is actually needed. Okay, so we will do a very small data set of regression, like just 3 points. Okay, just to appreciate this method. Regression application. So it is interesting that you are learning optimization for n-dimensional functions, moreover, especially working with two-dimensional functions, multi-dimensions. Okay. So here, regression is also like that. Suppose you have x and y. These are the data sets. Okay. And I am saying this to you already that an equation of the form, you already know why I denote y cap, y hat. Y hat, whenever I say it is a, I mean like I am trying to fit, okay, by regression. That is by y hat. And previous module, our job was to find which function was able to fit this data. Yes, but I'm giving it for free to you here. What I'm giving it to you? So I'm saying that W0 plus W1 by X is actually fits this data. Okay, this function fits the data. I'm already saying it to you. Now, your job is to find when the cost function or the residual is minimum. Okay, check if the cost function or the residual, okay, in a regression, does it attain a minimum? Attains a minimum, it is profitable to us. Okay, then it better fits. So our job is to find what are these like W0 and W1 quantities. Okay, these were our main targets, right, in the regression module to compute these points. Okay, such that the residual is minimum. Yes. So now we are seeing here using the multidimensional approach, okay, using a gradient and Hessian. Okay, so can you compute this? Okay, proceed with this one. Compute the gradient. But before that, let me write you about the error function. We discovered the error function, right? We talked about error function in regression. Like it will be 1 by n summation. So here it will be 3 points. So it is 1 by 3. And we have the summation. So this is your function I equals to 1 to 3. Yi is the points given to you minus the y cap. W0 minus W1 over x. And it will be squared. Of course, we thought that if you just take the summation of only errors without squaring, it turns out to be 0. Not a good candidate. To measure it, we have to take the square, which will take into account both positive and negative quantities. Okay. So can you actually write this up? So you know what to do. So you can replace yi. You have this xi and yi, three things, I equal to 1. This is like you can treat I equal to 1, I equal to 2, I equal to 3. Yes. For I equal to 1, you just put y value here, x value here. Yes. For I equal to 2, you put the x value and y value, which is here. So you will get a long equation, right? And that is your function you have to minimize. So you have to compute the gradient of E, set it to 0. Then compute the Hessian. Yes. And apply Sylvester criterion. Why you can apply Sylvester criterion here? It is a 2-dimension. It's in 2-dimension. For more than 2, we are not sure about Sylvester criterion. Only for 2-dimension you can apply the Sylvester. Okay. Can you? Okay, so for you to reduce your time, like you can compute this calculation at home, but I will just give you what is E. Okay, so you will get E to be this. So it's always not nice looking function. So there are some fractions as well. So you have to minimize this function. That's it. So this is you can see that for a small regression problem, you are getting such complicated equations here. So you can imagine, like if you take a lot of data points, you need to coding perspective. You have to code this up, no longer solve it by hand. So I am giving you this E function, and I am asking you to solve first step, the gradient to be 0. In that way, you can find the extremums. Okay, then check the minimization condition via Sylvester criterion because it's a 2-dimensional optimization problem. So nothing, like you have to find del 2E and compute the derivative of del 2E and check whether it is greater than 0. And the second derivative of the first variable, which is W0 here. And that should be greater than 0. Is it? After finding the extremum, check if these conditions are satisfied or not. then Sylvester condition is satisfied, and you can say minimum exists for this regression line. Okay. Yeah. So yeah, we are considering gradients, an introduction to gradients, and why it is important. Just before going to the gradient descent method algorithm. So consider this function f of xy, which is x square plus 2y square minus 2xy minus 2x. Okay. This function, if you visualize, it will be a surface in your 2D plane. Okay. But the moment you set it to some constant quantity, say 7, it will be just one level, like you are slicing. You are slicing your surface on the y-axis. So there you will get a curve. You will get a curve. You can understand. I think you can visualize this, right? Take a surface, visualize a surface like a carpet, folded carpet, okay? Not a carpet. Maybe a balloon. Yeah, maybe a balloon is a good example in your, but balloon is a 3D. I think you can take a carpet, okay? Take a carpet on 2D. Carpet is a 2D surface. Imagine the thickness, neglect the thickness, okay? Now you take the carpet and hold it in a parabolic way, like this, okay, like this. So this is, yeah, it makes it 2D or 3D, but if you take a slice, okay, if you take a slice of it, then you will get a curve. You will get a curve. Of course, a carpet piece will be there, but the moment you trajectory it, the boundary will be a curve. Okay, imagine. So if you set a surface equal to some constant quantity, you will get a curve. Okay. But if there is no constant quantity, it's a surface. So check it that if you set it to be equal to 0, equal to 7, sorry, you will get, put it in Desmos for quick visualization. So you'll get something like this. So our job is to find like dy by dx, like yes, compute dy by dx. What is dy by dx? It will be a slope. Tangent is like derivative is representing a slope, right? Dy by dx at a particular point, say -1, 1. Okay. X is -1 and y is somewhere 1. So somewhere here, okay. Yes. So what is the slope at this point we want to find? So for that, what you can do, you can differentiate this function. You can differentiate fxy, okay? Say, yes. So if you differentiate, how it will look? 2x differentiating with respect to y is a function of x, okay? So 2 into y is d by dx of y square. So what it will be? Yeah. Yes. Okay. Okay with it? Then what? Then how? Then what term will be? Y is a function. Keep in mind that y is a function of x. So minus 2x dy by dx, then minus 2 equal to 0. From this, can you compute dy by dx? Just keep common dy by dx and put everything on the right hand side. If you do that, check yourself that dy by dx you will get is 2y minus 2x plus 2 divided by minus 2x. Yes. Okay. So now you are in a state where you can put x and y values and it will give you the slope at that point, dy by dx. Okay. Okay with it. So our, as I told you, our job was to find the derivative at -1, 1. So can we do that? Dy by dx at evaluated at -1, 1. Just put the values in. So if you put -1, 1, it will be -2 times -1 plus 2 divided by 4. Yes, 4 times of 1 minus 2 of -2. how much it will be? 2 plus 2 is 4, my 4 plus 6 to 6. Okay. So dy by dx at minus 1 comma 1 is that means sorry, that means the slope is 1. That means what? It makes a 45-degree line because tan 45 is 1. Yes, tan 45 degree is 1. So you know, if slope is 1, it will make a positive angle with the x-axis. So how it will look? So it will look something like this. This is the tangent where this is theta like 45 degrees. Okay, pi by 4. So this is what the derivative gives us, an idea of a tangent. Okay. So what will be the slope of the normal, like normal to this tangent? Normal to this tangent means like a perpendicular line. Something like a perpendicular line, right? Okay. So before doing that, can I ask you to compute the gradient and see that the gradient is actually perpendicular to the tangent? Okay. Can you compute the gradient for this quantity? Grad f. Can you compute the gradient of this quantity? So it is dou f by dou x, dou f by dou y transpose. So what is dou f by dou x? Dou x minus 2y minus 2. Y minus 2x. Here, what should you get? So can you tell me here what's the value? Numerator is slowly minus. So there is no 2y term, is it? And what's the derivative at minus 1 comma 1? By 6. Yeah, maybe we'll take it next class. Maybe I did some mistake in calculation. So, but the why I was planning to show you this example is to actually see that dy by dx, when you compute the derivative, is actually the tangent, okay, which you already know, tangent to the curve, and you compute the gradient, okay, then the gradient will be perpendicular to the tangent, okay. So if you want to go to minimization, if you want to minimize some function, you can go along the gradient, okay, that's the direction. So therefore, in any optimization method, gradient comes in, okay, therefore gradient is important, okay. So ignore the calculation for now. I will take it up in the next class. I will see this. What? Thank you. So this main summary is